Today, we're going to do a CFD validation study on NACA 0012 section profile and compare our numerical results against experimental data reported by NASA organization. The point is that this is the pillars of aerospace and aerodynamics. So if you're interested in this field, you surely need to learn how to do a structured grid over an airfoil in the first step, and then you can get through the other applications. By the way, this study is going to employ a blocking technique, which gives us the chance to generate a structured grid with only 250,000 cells. So if you're a student or you're using a student version of ANSYS without any limitations, you can perform this simulation. Hello to our CFD community. Welcome once again to another free tutorial presented by CFD Land, this time about an airflow validation study. So, as always, we want to begin in Workbench workspace by drag and dropping the fluid flow using Fluent Launcher. We can start. So, in our initial step, we need to design the geometry model of the NACA 0012 section profile. So, this is where I want to Google the NACA 0012 coordination. I guess with this parameter, you can find this Airfoil Tools website, which gives us access to all coordination points. So it asks for some specifications. We do not have any camber, so put 0 in here. And for the most accuracy, we can increase the number of points to 200. And in this way, by closing the trailing edge, we can plot whatever we want. So after plotting that, you have all the coordinations on the right side that you can pick up from here. But I want to send it to airfoil plotter and define our exact chord size in here, which is about 1 meter, or in terms of millimeter, it would be 1,000. Then regarding the other parameters that are not going to change, we can simply plot, and after all, press CSV file of coordinates. And in this way, we can have the coordinate points of the whole airfoil using 200 number of points. So these are very accurate and we're going to use them, but we cannot simply put them down and import them into design model software, and we need to make some modifications. So for now, I just want to cut both columns and paste them in here. These are all extra. We do not want them. All we know is that this column represents the X coordination and this one is the Y value. So from now on, what I'm doing is exactly what is expected for design modeler template. We need to define all points for the software, and we also need to group them all together because these gonna be exactly represents one sketch. And in this way, we can put 1 for all, and the counter or the points is 1, 2, 3 to the end. So for the best, I guess it's better to select these two together and drop this exactly at the bottom of our columns. So as you can see in here, we've got an extra point, about 201 point. And in this way, you have to delete it. Otherwise, you'll face some errors during working. And it is a two-dimensional sketch. So we need to put 0 for all the coordinations. I guess in this way, we are now conformed to the default template provided by ANSYS in order to import any points into design model software. So after all, I copy them all together, and inside empty text file, I need to put them down. So I call this coordinates, and in this way, I can paste them all together. So I guess we can start with design model software right now. Very well. So in These are all the software. Before proceeding to import the curve and points, I just want to change my default unit to millimeters. And in this way, from now on, I can define all the parameters using millimeter units. So from the concept tab, you can find the 3D curve. For defining a curve in Design Modeler software, we have different types of definition, but what we want to use this time is from coordinates file that we already created. And then from this 3 dot bottom, we just need to locate this file that we created. It was called coordinates. So it was on base plane of XY, and in this way we could create the initial curve. So let's just zoom it out to see what has just happened. With just generating that, I can see the whole picture. This is what we created by zooming out. And if you pay more attention to the last part of it, you can see it is not a closed curve. And it means we cannot create a surface from this unclosed curve. So what I want to do this time is creating 2 construction points. One exactly at the trailing edge, and we need another one exactly at this very end point of our curve. To find out about the coordination of this point, we've got the whole points together. So this is exactly the last point, and we want to use this data to create another construction point. So this time from Create tab, I can find a point. I simply change the construction type and then definition to manual input. So what software asks is the exact coordination along X and Y axis. So based on the data, the X would be 999.753. And let's just put it down in here. And then along y-axis, it says that it's minus 0.36. So let's just put it. And here we go. You can see we could exactly reach the very end point of our curve. We need to create another construction point using the same method, this time exactly at the trailing edge, and it would be exactly on y-axis. So this represents another point. So up to now, we only have a line body, and we want to complete this using line from points tool. So what software asks is exactly the points that we want to connect together. And by holding down the control key, we can simply select them both and apply and then generate. So in this way, we could establish a full and closed curve. And this represents the whole NACA 0012 F-hole cross section. So let's use concept and then surface from edges tool to select these 2 lines together and generate the final surface body. So from now on, we do not need the line body anymore. By simply right-clicking and then pressing surface body, we can exclude that from a model. So there is a thing in here. From now on, especially when it comes to mesh generation part, we need to select these edges together. And in this way, we will have some difficulty in order to define the number of elements. So it's the best time to join them together using mesh tool that you can find beneath the tools tab. Exactly in here. And simply hold down Ctrl key to select these 2 together and apply this. And after pressing the generate button, you would see a bit and a slight modification, but it simply connect these 2 together. And it is of this sense, otherwise you will face different errors during the work. So we are done with the cross section of the airfoil, and now it's time to create the extended domain around it. So after pressing XY plane and then creating a new sketch, from the sketching tab, we can start a drawing using a 3-point arc. So what it asks, and you can see in this command bar, is exactly the first point, and this represents the endpoint. You can also use arc by center. Maybe it could be an easier way to do so. So the first thing it asks this time is the center of the circle. So we know that we have to exactly select the actually main origin. Just keep that in mind. You have the coordination of your pointer in this sidebar. So you have to zoom to select exactly the middle part. And with zooming out, we can go with the next point that could be exactly along the y-axis. You can see that a C sign above my pointer. After selecting this, the other point represents the other side. And in this way, we could create actually arc. So we need to continue drawing. This time I use the line tool, starting exactly from the endpoint using a horizontal line, and then another one, a vertical one, and finally we can close it. So before getting out from the sketching mode, I just want to use the dimensions tool and pick up semi-automatic, and in this way software show me what dimensions has to be specified. So the first one is the radius of this C-shaped arc, and the next one is the horizontal length. So as you can see, because we connected these lines exactly to the arc points, it does not ask from the other specifications. And by just defining two values, we will have a fully constrained sketch. So based on the data, because the domain must be very extended compared to the airfoil lens, and in most studies, it's between 10 to 20 times of the airfoil chord. So for this, we've got 14 meters. So in terms of millimeter, I have to put 14,000. And the next parameter is the radius of the arc, which is 10 meters. So once again, in terms of millimeter, it would be 10,000. So you can see the preview of our domain, and it is big enough. And it's time to convert it into a surface body. And this time we need to pick surfaces from Sketches tool. So all you need to set is a sketch one and apply this, and we do not want to add it to the previous surface body that we created. So if you keep add material and press generate, you can see what's going on. This is our full body, and this represents the whole domain. So you already know in any CFD simulation, we need to only keep the fluid domain and subtract the solid part. And to do so, we have to follow the create tab and then Boolean tool. So let's just change the operation to subtract. Our target body is the big domain, and our tool body is the airfoil in the middle. And we do not want to preserve the tool body. So after pressing the generate button, you can see the airfoil has successfully deleted from our computational domain. And in the tree outline, we only have one surface body. And you can also change the region to a fluid region just here. So we can say you're done with the geometry step, but in order to produce a fully structured grid, you have to do and split the body into pieces. And this is called blocking technique. So I want to begin drawing these extra lines on a new sketch. So after selecting XY plane and then sketch 2, from a sketching tab, this time I can pick up line tool to start my drawings. So the first thing that I'm gonna create is a line starting exactly from the topmost point of our domain, even out of it, and continue that to the bottom one. Just keep that in mind, it must be vertical. This was the first one, and we also need another line somewhere near the leading edge of the airfoil. And this represents our next split. And finally, we need another one exactly on x-axis. So we're gonna use them to split the domain, but for now we have to adjust exactly their position using dimensions tool. So this time, for example, you can keep with length or distance tool, holding down Control key and select the parameter that you wanna define. But you can simply also use semi-automatic, which shows you which parameters has to be specified. So for example, the length of this line is not important to me. By right-clicking, I can skip that. Next, it asks for the length of this line. Again, it does not matter, and also the length of the other one. But what does matter is the distance between these tools. For example, once again, this horizontal line does not matter, but it asks for it because it's just gonna have a fully constraint one. And the important one that it asks is the distance between this vertical line and our y-axis. So this does matter, and by clicking, I want to define it. But once again, as for the length, I skip that simply. The next one also. And the most important one, once again, is the distance between this vertical line and y-axis. So all in all I want to set is just the distance between these two lines and the vertical axis. So based on the data, it must be close enough to the leading edge. I want to define, let's say, about 1.1 meter, or in terms of millimeter, it could be 100. And then the next one must be exactly on the trailing edge, and we already know the distance. So we are done with the blocking, but before leaving this, we have to split the body into pieces. Right now, as you press this surface, you can see one as a unique part. But after you follow the face split tool and select your target face, which is this, and then your tool geometries that are these lines, and in order to select them, you have to pick up the H selection tool, holding down the Control key, and select them all three together and generate that, you can see the difference. So you may have not seen anything in here, but after selecting the face selection tool, you can see exactly what is going on. And this gives us the chance to define separate number of elements for every part of this domain. And in this way, we can establish a fully structured grid. So we are done with geometry, and hopefully we can continue into ANSYS meshing. Alright, so before proceeding to ANSYS meshing, I just want to mention a major reference. So on the website of NACA, you can find a comprehensive study delving into tolerance models, and if you scroll down, you can see different reported results, but you can also see the Latson worst data. So these data are all experimental that were investigated on a NACA 0012 cross-section area at different angles of attack. As you can see in here, the variables are alpha, the lift coefficient, and also the last column represents the drag coefficient. What we're gonna investigate is the airfoil performance exactly at zero angle of attack. So within this column, we guess this is the closest one to zero angle of attack, and we're gonna use that. The other important thing about this is the Reynolds number. So it shows the Reynolds equals 6 million, and we have to keep that into our calculations from now on. And before proceeding into that, I want to give you some explanation about the calculations that help us through the way. So through our website, you can see the CFD calculators up here, and I need to use them. So first thing that I want to need is the Reynolds number calculator, and next it comes the Y plus. So let's start from Reynolds number. We already know what I want to achieve from this calculator is the velocity inlet. So I want to calculate the velocity from the Reynolds number, and it's gonna be an external flow. So as we saw in the Latson reported data, the Reynolds number in this experiment was 6 million. And then the characteristic length when it comes to airfoil is its core, which is 1 meter. The density of the air is 1.225 kilogram per cubic meter. And finally, the dynamic viscosity must be set based on the data that we're going to use in ANSYS Fluent. So here we go with dynamic viscosity of the air at a standard temperature. And as soon as you press the calculate button, you can see the velocity of our experiment, 88.65 meters per second. So this gonna help us when it comes to calculating the y plus. In the y plus calculator, once again, we need to change the external flow. And the characteristic length once again is 1 meter with the same density. The Fourier steering velocity is now proven to be 88.65 meters per second. And also the density, the viscosity of the air that we're gonna use. So it completely depends on our accuracy of simulation. If you aim to use K omega SSD turbulence model, for example, you need to keep y plus value below 1. But in this case, we're going to use Escalart almost 1 equation turbulence model. And this means we can keep the desired y plus below 5 or 4. So by pressing the calculate button, what software gives is exactly the estimated first cell thickness, which is very important for every aerodynamic analysis. So what it shows is that in case we want to have a y plus value of 5, we need to have firstly a thickness about 0.02 millimeter. And if we decrease that to 4, you can see it just get to about 0.01 millimeter thickness. So keep that in mind. We're gonna use it in our calculation during generation of the grid. Let's get back to the software. I wanna begin from the mesh. And first thing that I wanna set is a face meshing in all faces by following insert and then face meshing. So all it asks is the faces that we're gonna apply this tool, and simply we need to select all together and apply. So from now on, the software will try to use map mesh, and it means it's gonna use quadrilateral cells in every places. But in case there would be any difficulty, it just turns into triangles, which is not our preferred type of elements. So let's begin by inserting values on all edges. I want to start with sizing of these horizontal lines, these three. So picking up the edge selection tool and holding down the Ctrl key, I simply select these three together and apply. My type of definition would be number of divisions, and for this, I'm going to use 100 number of elements. So what we know is that when we get closer to the airfoil, we need denser grid, and in this way, we can manage the total number of elements and make it more efficient. So first thing, turn off the capture curvature to make the behavior too hard, and this dictates the software to only follow a lead. And then from bias type, I've simply select the first type, which is denser just in one side. And for bias factor of this, let's say 100 could be good. So what it means is that the first and the smallest element is 100 times smaller than the biggest one. But what we can see in the preview is that it's not what we wanted. We aim to have this grid exactly in the vicinity of the airfoil. And right now, only this edge represents the correct direction. So from the reverse bias, we need to select these two reversed ones and apply them. And in this way, we can see what is going on as we get close to the airfoil. So next it comes another sizing. This time it could be on these curved ones, and we just only forgot something in this mother software. As you can see, we've got an extra edge in here, which actually makes it worse, and we need to get back to this mother software to modify this. So once again, let's just quickly get back to this mother software. And in this panel, once again, we need to use the merge tool here. And what we're gonna join together is just these three edges. So select these three together to apply. But let's say 4 in total. So let's just check it and simply apply them all. So now we can get back and continue in ANSYS meshing. Very well. So you remember we were doing base curved sizings, and for this we have to get back to sizing. For the geometry, we have to pick these 4 edges together, and they must have equal number of divisions. So once again, we change the type, and this time we have to have 100, but without any bias. So just stick to hard behavior, and in this way we can have a very uniform distribution on the leading edge of our airfoil. So next it comes the other edges. I guess we need to create a separate one, a separate sizing, this time for these edges together. So there must be equal number of divisions for these 4 edges together. And for this, maybe this time we can have a 300 number of divisions. And this is the place that we expect to see flow separation, of course, in higher angle of attacks. So we do not need to apply any bias, and it seems to be a uniform and well-structured grid. And finally, we get to the most important part, which is about these vertical lines together. So this, I guess, 7 lines together represents the vertical ones. And why I put emphasis on that? It is exactly the place that we have to be more accurate, because the number of elements and the distribution of the elements here does matter, especially near the walls of the airfoil, because it is exactly what we seek. It is the y plus value that comes in. And for these phones, I want to employ 250 number of elements. So for now, it sounds uniform. So we need to apply a bias as well, because these outer walls does not matter to us. And what is important is exactly upon the walls of the airfoil. So I have one side density grid type, and for bias factor this time we tried and examined different cases, and in all we came to the conclusion that 5 to the 10 power 5 would be appropriate. So you can see, for example, the result. It is very, very thin. But before proceeding, we have to reverse the incorrect ones from reverse bias option. So this time I have to pick this one. This 3 edges represents the reverse type, and I guess now we're totally correct. So let's generate to see what will happen. Here we go with the final grid. As you can see, we have a great distribution of elements in the most efficient way, with only using 250,000 number of cells, which means you can apply and create this grid and then continue in the solver using ANSYS Student version regarding its limitations. So we have a very great distribution over the walls of the airfoil, and what is very more important is the first layer thickness that you can see in here. So this was our aim, and I guess using this tool we can see exactly the distance between these two nodes, which is about 1 to 10 power minus 6 or 1 micrometer. So it was exactly what the calculator suggested, and we can say during our simulation the y plus remains below 4 at least. So I guess we are done with our first mission in ANSYS meshing, but before leaving we have to label all the boundaries that we want to use in the solver. So I pick up the edge selection tool and start from this edge, and these all gonna represent our inlet. So I pick them all together, And then by right-clicking, you can follow create an installation and simply call this Inlet. Then we've got these two lines together, which represents our outlets. And I guess finally, we have to set a name for the walls of our level. You can also pick up the bar selection tool, starting from a left point and draw a box, and all the edges inside that would be selected. And this gonna be our level. We can call it NACA 0012 wall. So in the three outline, let's just check them once again. This all together represents the inlet. This is our outlet, and this gonna be our airfoil wall. So we are done with ANSYS meshing as well. Now we have to update it before continuing in the solver. There you go. By double-click on Setup, you would see the Fluent Launcher. Do not forget to activate double precision, which gives us higher accuracy because it will calculate all the variables up to 60 decimals. And then based on your system configuration, you can employ a higher or lower number of processors. I want to begin a work in ANSYS Fluent with the warning that you can see beneath the console command. So it represents that we only have one region, and this is a solid region, which is not a preferred one. So from cells and condition, the first thing that has to be changed is the fluid region, and from now on, there wouldn't be any problem regarding this warning. So let's get back to General tab, where we specify all the general assumptions of our solution. First, it comes with pressure or density-based solver. We are simulating flow at 88.625 meters per second velocity. If we assume a standard air properties, the speed of sound would be 340 meters per second. So we can simply calculate the Mach number of our case, which is 88.65 divided by 340. So we can say a Mach number in this case is 0.26, and we are simulating the transient flow. And in general, in any cases that we can neglect the compressibility effects, we tend to use pressure-based solver. So in aerodynamics, if the Mach number is below 0.3, the air is considered incompressible. The density doesn't change Mach. And it means we can use pressure-based solver type. In simple words, we are excluding all the derivatives of density from our Navier-Stokes equation. Then it comes the time mode. We want to investigate the performance of the airfoil as soon as it reaches the steady state time-independent condition. So we do not need to change it. And finally, we actually do not want to consider the gravitational acceleration effect at this aerodynamic analysis. Next, it comes the models tab, and it starts with viscous. So this panel represents the viscous turbulence model that we're going to use. Because we are using pressure-based solver, ANSYS Fluent gives us wide range of choices, but in the current simulation, the model that we're going to use is Spolart-Almaraz 1 equation model. This is the gold standard for external aerodynamics, airfoils, and wings. It was specifically designed by Boeing engineers to solve flow over wings efficiently. It is faster than K-epsilon and gives excellent results for attached downward layers. But we also have another section when we assign Spolart-Almaraz model, and it is called Spolart-Almaraz production. So this is very important subsetting for aerodynamic analysis. And let's say for this current simulation, we're going to use a strain or vorticity based. So by selecting a strain or vorticity based model, we are telling Fluent to look at both the stretching, the strain, and rotation or vorticity of the flow. And this prevents the solver from generating unrealistic turbulence at the leading edge, making drag and leap results much more accurate compared to experimental data. So this was all we had to set for viscous turbulence, and I guess we have nothing to do with this panel, so we can simply close that. Now let's just check predefined materials. We've got error by default, and let's just check the properties. So as we use in our calculations, the density of air at a standard condition is 1.225 kilogram per cubic meter, and we need to change a bit the viscosity. So as we said, it would be 1.81 to the 10 power minus 5 kilogram per meter second. And in this way, it completely matches our calculations. Next, it comes the boundary conditions. So I want to begin from our inlet, which is colored in blue, and this is schematic, and it has velocity inlet to a boundary condition. So we already have the exact value of velocity magnitude, so this could be the best boundary condition type to us. As you already know, the velocity magnitude is 88.65 meters per second, equal to Reynolds number of 6 million. And then we better use another type of velocity specification method, and maybe magnitude or direction could be the best, because we assign these top and down walls as inlet, and in this way we will face some errors if we want to inject air from these boundaries as well. So it would be much better to use magnitude and direction, apply the whole incoming airflow through the x direction. And in this way, we can avoid any divergence and also instability from our calculations. And finally, we've got a turbulent viscosity ratio down here, which gonna be 1. This is a very low value. It represents clean air, mimicking a high-quality wind tunnel where the incoming air is very smooth with little disturbance. And this correctly represents our wind tunnel condition. Next, it comes the outlet, which has pressure outlet type boundary condition, and it is colored in red at the back side of our domain. So by applying gauge pressure of 0, we tell the Fluent that there wouldn't be any pressure gradient at this specific boundary. So in simple words, it will have 1 atmosphere pressure, exactly equal to surrounding air. And you can also set 1 for turbulent viscosity ratio once again, but keep that in mind. It is set in case there would be any backflow. And finally, the wall of the NACA 0012 airfoil, and we already know that it's a stationary wall with no steer condition applied. And in this way, we can say we are totally done with setup section. And let's just jump to methods. So here we go with a pressure velocity coupling scheme. Once again, due to actually activating of a pressure resolver, ANSYS offers us 4 distinct choices for pressure velocity coupling. In this try, we're going to use the coupled algorithm. It is a modern standard. It solves pressure and velocity equations together simultaneously. And it uses more RAM, but it reaches the final answer much faster and handles the airfoil mesh better than other schemes. And then for all discretization methods of every equation and also pressure gradient, we're gonna use second order and second order often. Because this is mandatory for any validation work. First order is too blurry or diffusive and will give us the wrong Dirac coefficient. So always for any validation study, it's better to use second order often to keep accuracy as high as possible. Next, we have to check primary convergence criteria, what we call them residuals. Well, think of residuals as your simulation's way of showing you how well it's solving the equations. Every time Fluent runs an iteration, it's trying to solve equations for mass, momentum, and energy conservation. The residuals show us how much error is left in these solutions, basically how far we are from perfect conservation. When you start the simulation, these residuals usually start pretty high, but as the solution progresses, we want to see them dropping down. In most cases, we're looking for residuals to fall below 10 to the power minus 3 or even minus 4. This is like saying our error is less than 0.1%. By default, Fluent sets a specific convergence criteria for different equations. These are absolute criteria. Think of them as the finish line. When our residuals drop below these values, Fluent considers the solution converged. However, this is really important to understand. These default values aren't always what we need. For higher accuracy simulations, we might want to tighten these criteria. Now, there's something really important I want to understand about convergence. You will know your solution is converging when these ratios starts leveling off. They're not dropping anymore. But here's a pro tip. Don't just rely on residuals alone. It's good practice to also monitor things like mass flow rate or pressure drop to make sure they're stabilized too. Very well. Now you know what are these criteria that we define in here, but in this try, we do not want to rely on residuals. Instead, we're gonna monitor our output parameters, which are drag and leave coefficients instead of residuals. So I simply unchecked all of these boxes, and we do not want the solver to automatically stop the solution. And instead, we want to define drag and leave coefficient. This must be done through report definition section. So by right-clicking, you can define a new force report type, and in here you will find drag and lift. So let's start by the drag force. First of all, I just call this CD. It stands for coefficient of drag, and our output type would be drag coefficient, and it must be measured on the walls of our airfoil. The most important thing lies in the force vector. Of course, in our current case, the angle of attack remains 0, which means the airflow will be exactly along the x-axis, and we already know that the drag coefficient is exactly along the wind direction. So x is exactly true, and we do not need to change it. For the next report, I want to follow the same path, this time select lift, and call this CL. The thing is, once again, the angle of attack is 0, and we already know that lift is exactly the normal vector compared to the wind flow direction. So it must be along the y-axis, and the default value represents the same thing. I put emphasis on this because if you're gonna continue simulating, testing the different angle of attacks, you have to put the correct force vector in here. And finally, what you have to give more attention to is the reference values. So these are the parameters that really affect our calculation because you already know the formulation of drag and lift coefficient. There would be some constants that we need to set. And when it comes to airfoil simulations, this area does matter. This is exactly the characteristic length that we use and deploy in our formulation. And in most studies, we set the chord length as the projected area. So 1 is the correct value for our case, which has 1 meter chord. And finally, from initialization section using a standard initialization method, I want to put this initial guess into our Gorenio equations. And finally, from run calculation section, define an appropriate number of iterations to start. The thing is, we're going to monitor the drag and lift coefficient during this solution, as you can see. And as soon as they reach a constant value, or better to say stabilized, we can stop the solution to check our final outputs. After about 160 iterations, I stopped the solution manually. You can see a constant value, which is reported by drag coefficient, and also the lift coefficient report shows the same actually trend. And through the results, you can see we can also continue for more accurate results, but we already reached the condition that we aim to achieve. So I want to start post-processing with actually measuring the drag and lift coefficient to compare to Latson experimental data. The post-processing stage is where we act as engineers and deliver a verdict on simulation's accuracy. So we want to start with comparing our computed results to the experimental from NASA wind tunnel test. So if you remember, for this Latson data, for this specific angle of attack, the drag coefficient is about 0.1. That we know it must be zero for, let's say, zero angle of attack due to symmetrical shape of NACA, 0.012, it must be zero. And then for lift coefficient, it's about 0.0809. So let's just check our results together. First, it comes the lift coefficient. By right-clicking, you can compute that. And you can see it is somehow very close to zero. And it makes sense because we expected to see zero value for this parameter. And then for drag coefficient, which would be more debatable, it's exactly what we saw in the wind tunnel test of Lapson. And this represents even below 1% of derivation. And it proves that Spolart-Allmers is a very accurate and powerful tools model that we can use for most of aerodynamic analysis. So this matches the experimental data, and we already can just say we are completely validated the experimental data of Latson. So let's check the graphics, and let's start with contours. In this panel, you can display any variable that you're interested to visualize. So maybe it's not a bad idea to start with velocity distribution over our whole domain. You can select any boundary that you want to measure, and you can just keep it unselected for all, and in this way we can display it over the whole domain. So the velocity contours for Fluent provide the visual proof for why the forces are what they are. So in this figure, what you can see is exactly the stagnation point at the very front of the airfoil, where we call the leading edge. It's a small blue region where the air stops and splits. Most importantly, the contour shows perfect symmetrical pattern both from the suction side and pressure side of an airfoil. And this pattern exactly why we expected to see the lift coefficient of zero. And this is the visual confirmation that the upward and downward forces are balanced, leading to zero. We can also check the pressure distribution. It can give us another verdict. So this plot is like the fingerprint of the airfoil, showing us exactly how the pressure on the surface creates the aerodynamic forces. At the leading edge, exactly in the vicinity of this point, this is a sharp pressure spike. And this is the high stagnation pressure where the air impacts the wing. As the air flows over the curved surface, both the suction side and pressure side, uh, we can see that it just splits and speeds up, and this matches with the velocity contour that we saw in the previous try. So this pressure drop creating a suction, and this is a key evidence from these visualization tools that we have that the pressure distribution is identical for both the upper and lower surfaces. This means that the suction on the top is perfectly cancelled out by the suction on the bottom. When all these pressure are added up, there is no net vertical force, which once again confirms why lift is zero. So I suggest you to perform other simulations using another angle of attacks. The mesh is established, fully structured, so it can satisfy your need, and you wouldn't face any divergence through your solution. I hope you find this tutorial helpful. In case you're interested in more free tutorials, do not forget to subscribe and leave your comment.